All right, welcome back, everybody. This is it. This is the very last lecture of the course, section 11.11. That's a good number to end it on, right? Good news is this lecture is actually relatively short. The bulk of what we need here was all talked about in section 11.10. So that's the big one. Let me go ahead and pull up the slides and we'll get started. Okay, this section is quite literally about applications of Taylor polynomials, the things that we talked about in the last section. The overview is really quite short. Let me just say there are innumerable applications of these tools developed in the last section. We don't have time to detail all of them here, or even most of them here. So you're encouraged to read the textbook if you want to see other applications, because there are a lot of them in there. But my hope is that at least you can see that there's utility in these tools. So utility in these tools. Remember, these are tools that you are allowed to use, and I'm hoping that you'll remember that they exist and that you can use them in your future endeavors later on, all right? We're only gonna cover one application. That's just the most general application, which is approximating functions by Taylor polynomials. So literally a specific example of what we learned in the last section. The techniques that we're going to use are similar to what we did in the previous sections, just in this new context of Taylor polynomial approximations. All right. Um, so what we saw previously was that we can approximate functions that have Taylor series representations by using Taylor polynomials. That was the whole idea, right? We also want to know how good our approximation is. This has been a constant question since even Calc 1 or even pre-calculus. Hopefully your instructor was emphasizing the difference between approximations and equalities because that's like a core of calculus. So we want to know how good our approximation is when we're using a Taylor polynomial to approximate. And we've got three possible methods for doing so. If we have a computer, we can graph the size of the residual to estimate the error, basically have the computer graph that series. If your series is alternating, you might be able to use the alternating series estimation theorem, and you'll know that you can always get a bound on the error by looking at the size of the first neglected term. And then in all cases, we can use Taylor's inequality. So a lot of times Taylor's inequality is just the like the go-to because it always works. But just because something always works doesn't mean that it works the most easily. So I don't want to discount possibilities one and two. Okay, so let's do an example. Let's look at a simple function. Let's approximate the function cube root of x by a Taylor polynomial of degree 2, so that's parabolic, at the point a equals 8. So we're going to center our approximation at the point 8. And then the question is, how accurate is this approximation on this interval? So when x is between 7 and 9. So essentially, if you move 1 unit away from the center, how good is your approximation? That's the question. Okay, so first thing is we need to actually compute a Taylor series. So really we only need a few terms because we're going to do a degree 2 approximation. So we only need to compute up to like the third or fourth derivative. Third derivative. Yeah, third derivative. We're going to need the third derivative to use Taylor's inequality. But since we're just doing a degree 2 approximation, we would only need the first two derivatives. So the technique is identical to what we saw in the last section. You just compute the derivatives, and then you evaluate those functions at the center. And those will be part of the coefficients of your Taylor expansion, your Taylor series representation. So putting these together, we get this, that cube root of x is approximately equal to its second order Taylor polynomial. And that Taylor polynomial is given by this formula. And we have all of the things that we need for that formula. So this becomes this, or sorry, this becomes this becomes this, and this becomes this. There it is. So this quite literally is the formula for our parabolic approximation of this function at the point x equals 8. And we can use that approximation near the point x equals 8 to get approximate values of cube root of x. So like if you want to know what is the cube root of 8.2, Well, you can use this instead. Just plug in 8.2 and it'll give you an approximation to some degree of accuracy. Just to see a picture of it, let's take a look at a Desmos example. Give me one sec. There we go. Okay, here we go. Again, you can follow along using the slides. Just follow the link and it'll take you right to here. So the green curve is cube root of x, and we're centering all of our analysis at this point. So that's, again, remember, the center is basically where we're putting all of our focus, right? So all of our analysis is really concerned about this point right here. There it is. This is the second order Taylor polynomial approximation. It's this blue curve. Notice it's a big parabola. It's a big parabola. This is the leading coefficient of this parabola, so -1/288. So it's definitely a parabola that should open downward, and it's going to be stretched wide because this leading coefficient is less than 1 in size. That's why this looks like a pretty wide parabola. But again, all of our analysis is focused on this point right here. So you can forget everything else away from this point, right? And the question said that we were only concerned about x values between 7 and 9 inclusive. So this window is basically what we're focusing on, okay? And notice just by looking at it at this point, you can see that our polynomial approximation is pretty dang close to what the actual function looks like. And if you zoom in, it takes a while before you start to see a difference. There it is. Okay, there's the difference. So again, these are not equal to the function. They are approximately equal to the function. They're approximate, right? They will be equal to the function at the center. So at the center is where these two things cross. Let me zoom out again here. There you go. Okay, now let's zoom in on this instead. There we go. So at the center is where they cross. But then if you go a little bit away, oh, I just maxed out Desmos, my bad. Let me zoom in on a different part. That's a little bit further away. See, the further away you get from the center, the worse the approximation gets. Geez, I got to zoom out a lot to even see where I'm looking at. Here we go. Here, I'll try to go to the edge here. The edge will be where the accuracy is the worst. There we go. Okay, so we've got a Taylor polynomial approximation here of our function. It's accurate to some degree. The next question is, how accurate is it? In other words, how far off are these two functions? How big is this gap? What's the biggest this gap could possibly be? Even looking at Desmos here, this can give us a kind of a decent idea. Oh, yeah. See, look, it's equal up to 2 decimal places here, starts to deviate at the 3rd decimal place. But again, Desmos itself is approximating this green function. It's approximating it. It's approximating this green function. So, and Desmos only lets you go up to about 3 to 4 decimal places before the tolerance is exceeded. So we don't want to be constrained to Desmos's limitations. We want to have a more general theory that'll let us investigate approximations and their accuracy in general. All right. So now that we've got this approximation, I want to know how far off it could possibly be. So let's go back to the slides and continue from there. All right, so there's one little catch here. How can we actually find an upper bound on the error? And looking at the formula for the approximation immediately, you might be tempted to think of using the alternating series estimation theorem. But the series is actually not alternating. It's not alternating when x is less than 8. Let me go back to the formula here. So notice here, it's positive, positive, negative. It's not alternating. If this were a negative, then it would be an alternating series, but in this case, it is not an alternating series. Yeah, so we can't use the alternating series estimation theorem because it's not actually an alternating series. But luckily, we've got Taylor's inequality to come in and save us. So remember, Taylor's inequality is this formula, and when we plug in our information, this is what we're going to get. So the residue when n equals 2 has to be smaller in size than this expression here. 2 is n, so 2 plus 1 is 3. We get 3 factorial, and this just simplifies to this. So what we know is that the size of the residual is smaller than this value. We just need to find a suitable m. So we need to find a suitable upper bound. This is actually why we calculated the third derivative. So remember, Taylor's inequality says that you need the third derivative, or the n plus 1th derivative, to be bounded. So we computed the n plus 1th derivative, the third, which is this. And now all we need to do is we need to think about this function and try to, if we can, try to find its maximum value on this interval. Really, that's the ideal setup. If you can find the maximum value of this function on your given interval, that's the optimal choice of m. Optimal choice of m. And this kind of harkens back to when we were looking at approximate integration and you had to find that upper bound m back then. It's the same idea there. If you can find an actual maximum, then use that, because that'll be ideal. If you can't, you're just going to have to get like a decent upper bound. That's all you can do. But luckily in our case, we've got a nice continuous function that is actually decreasing on this interval. So that means that it must take on its maximum at the left endpoint when x equals 7. So you plug in x equals 7, you get this value here, and a calculator gives you an approximate value of 0.00207. So that's what we're going to choose to be m. We're going to choose m to be this. This is a decent choice. Okay. Now we've figured out this part, right? Now we need to get a value for x minus 8. And remember, this is an inequality. Inequalities are more flexible. They're not like equalities where you're stuck, like you're rigidly tied to equality. We just need to find an upper bound for x minus 8 cubed. Well, how do we do that? We kind of investigate the bounds that we're interested in. So since we know that this is the interval of interest, if we subtract 8 from all sides, we get this, and that's equivalent to saying this. There you go. So you can, I'll say you can always do some kind of algebraic manipulation to get to something like this. You just have to be careful if your center is not right at the center of that interval. You'll have to pick the smaller one, the smaller interval that will work. This is an idea that you kind of see back in Calc 1. So hopefully your professors talked about the epsilon delta definition of a limit at a point. And you have to basically pick the smaller of the deltas when your function is not linear, the smaller of the choices for delta. This is the same kind of situation here. Whatever you pick, you've got to make sure that you're picking the smallest delta. I know that's a bit confusing, but in this case, it doesn't matter because our interval is symmetric about the center that we're given. So these numbers will always end up being opposite of each other, and then you'll be able to get this. Okay, so what we know here is that the distance between x and 8 is less than or equal to 1 on this interval. So that means that x minus 8 cubed is less than or equal to 1 cubed. So at this point, we can actually just plug in what we know. So we know that this is going to be less than or equal to this value. We found a decent choice of m right here. And we know that x minus 8 is less than 1 or equal to 1. And then this gives us this right here. Okay. So what this is telling us is that the error involved, the residual involved, is smaller in size than 0.0004. So that means that this approximation is accurate to within a tolerance of plus or minus 0.0004 when x is within these bounds. So that's not too bad. That's not too bad, because what this means is that, hey, if you don't want to deal with this function, you can instead deal with, where'd you go? Deal with this function, and your error will only occur in the 4th decimal place or above. Pretty nice. Pretty nice. If all you need is like 3 decimal places of accuracy, you might as well just use this parabola instead of using a cube root of x. You know what I mean? That's the idea. Okay, so let's see. We got that, and that's it, my friends. That is it. That's the end. So congratulations. This is the end of Calc 2. We have covered all of the content of the course. I just want to say congratulations. I know that it's a difficult course. It's a long course. There's just so much content and information packed in. Um, it's just so amazing though. So I hope you enjoyed it at least a little bit. I personally did not enjoy Calc 2 that much when I took it as an undergrad, but I fell in love with it when I became a graduate student and then when I taught it later on. The concepts and the theories in it are just so phenomenal and applicable just all over the place. So I'll leave you with a quote from one of my favorite mathematicians, George Cantor. It's the essence of mathematics lies entirely in its freedom. So I'm hoping that through this course, maybe you've kind of seen that mathematics is not just a rigid, unflinching, boring, rigid like process. It's a freedom. There's freedom involved. It's a creative process. Oh, but before I say congratulations and it's the end, I do got to say, let's play one last time. We're going to do activity 11.11, and you're basically going to practice approximating a function using Taylor polynomials. Um, but on that note, yeah, that's about it. So thank you all again. It's been an amazing journey, and I hope that I get to see you all in later math classes as well. And I hope that you keep studying math, keep studying math. Remember, you can go down the rabbit hole as long as you want to. You just get to decide when you're ready to jump off. All right? There is no highest math class. It keeps going. It keeps on going until forever. All right? So I'll stop rambling once again, one last time. Thank you all. Good luck in the future, and I'll see you around.